So this is going to be our probably penultimate lecture on smooth analysis. So where you have adversarial input except slightly perturbed by nature, and you want to prove positive results under only those relatively weak assumptions about the amount of randomness in the data. And so the application of smooth analysis we're going to discuss today is to something called Pareto curves. And so let me open the lecture by explaining one reason why you might care about Pareto curves. Namely, it turns out there are some pretty neat algorithms where the running time is actually governed by the size of a particular Pareto curve. So let me remind you about the knapsack problem, which I hope you've all seen before. So this is a well-known NP-complete problem. So the input consists of n items, each of which has two positive parameters, a value and a weight, or a size. Okay? So there's values, v1 up to vn, and I'm going to call them weights. They're often called sizes. And then finally, there's a knapsack capacity, capital W. Okay? And the goal is simple enough. You want to take as many items as possible, so you want to maximize the value. So you're going to pick a subset S of the items. You want the total value to be as high as possible. The constraint is that the item should fit in your knapsack. That is, the sum of the weights in the set that you choose should be at most capital W, the knapsack capacity. Okay. So that's the knapsack problem. When you first saw this, you may have been told some hokey story about a burglar, who wants to sort of put a bunch of items in their knapsack and make away with as much loot as possible. But it's actually a very fundamental problem. Whenever you have a limited amount of a resource and you want to use it in the optimal way, that's pretty much a knapsack problem. Okay, so it comes up all the time. All right, so I'm going to tell you about a knapsack algorithm that you probably haven't seen before. And to tell you about it, I need to talk about Pareto curves. So consider two different subsets of items of a knapsack instance, S and T. We'll say that a subset of items S dominates another one, T, if, on the one hand, you get more value from S, but on the other hand, the total weight consumed by the items in S is at most that of T. Okay? So items have two parameters. So there's two axes along which you could measure the quality of a solution. How much value do you get and how much of the knapsack it picks up. So S dominates T if it's better simultaneously according to both metrics. Okay? Both more value and smaller weight. So clearly, S basically renders T moot. Right? There's really no reason to ever think about the feasible solution T. It's just, you'd always want to use S instead. Okay? And the Pareto curve then is just the set of undominated solutions. Okay? So you might want to think about drawing a graph where you have the total weight on the x-axis, the total value on the y-axis. And basically, if you're dominated, it means there's a point to the northwest of you. Okay? There's something that has both less weight and higher value. And if there's nothing to the northwest of you, then you're undominated. So we're expecting a Pareto curve to look something like this. Okay? And maybe these would be 2 points that are dominated. Okay? There's a point to the northwest of each of these. You've actually seen this concept before in this class. It's been a little while, but in lecture number 2, we talked about 2D maxima, where you're given points in the plane. We wanted to compute the undominated points. Exactly the same thing. The only difference in the picture is that it's reflected around the y-axis because of the way we're labeling things this lecture. Okay? So that's it. It's just the same thing as saying if you plotted the total value and total weights of every subset of items, you'd just be looking for the maxima of those 2 to the n points. Okay? That's the Pareto curve. Any questions about that? Okay. So let me tell you about an algorithm. a knapsack algorithm which you probably haven't seen before. But that is useful. It's practically useful. It just happens to be sort of underrepresented in undergraduate classes and textbooks. So a knapsack algorithm. So step one, I'm just going to state it at a high level. I'll leave the detailed implementation to homework 7. Generate the Pareto curve. Okay, so enumerate all of the undominated solutions. And then amongst those, just find the one that has the highest weight that gets as close to filling the knapsack as possible. Okay? Or rather, among everything that fits in the knapsack, in the Pareto curve, just pick the one with the highest value. Okay? So return max value solution in the Pareto curve with weight at most capital W. Notice that the Pareto curve doesn't reference the knapsack capacity capital W. Okay, so the Pareto curve depends only on the VIs and the WIs. Once you then know the knapsack capacity, it's sort of obvious which one you want to pluck out, right? You throw out everything that doesn't fit among those that are left. You take the one with the highest value. Okay? All right, so it's clearly correct. Okay? The only issue would be by restricting yourself to, so these are called Pareto optimal solutions, okay, points in the Pareto curve. So I'll use the word Pareto optimal over and over again in this lecture. So the only thing to prove is that there's no loss of generality restricting yourself to Pareto optimal solutions, but that's obvious by the definition of being dominated. Right? If something's dominated, you can throw it out. It's no big deal. You're definitely not throwing out an optimal solution. Okay? So correctness then is clear. So what about the running time? I mean, it is an NP-complete problem after all. So to implement, the way you want to do it, and so the main thing I want to emphasize here is this: there's no explicit dynamic programming in this algorithm. And my guess is every knapsack algorithm you've ever seen, and you may have even seen more than one, they always have explicit dynamic programming, and here you don't. So the way to do this is you want to generate a sequence of Pareto curves corresponding to prefixes of the items. So you order the items in an arbitrary way. You first generate the Pareto curve of none of the first 0 items, so that's just the empty set. Then the Pareto curve of the first item, the Pareto curve of just the first 2 items, first 3 items, and so forth. And I'll let you think about it a little bit offline this week, but once you've computed the Pareto curve of the first I items, it's conceptually very straightforward to then compute the Pareto curve of the first I plus 1 items. Okay? So to implement, iteratively generate, I'll call them the PCIs, where PCI equals Pareto curve of the first I items. Okay? And what I'll ask you to prove on the homework is that you can implement this algorithm in time proportional to the sizes of the Pareto curves. Okay? So basically, I mean, the hint is to generate the I plus 1th Pareto curve from the ith one. Turns out all you need to do, basically what you want to do is you want to keep the Pareto curves sorted by weight, let's say. And then to get the next one, you just make 2 copies of the current Pareto curve, one without item I plus 1, one with item I plus 1. And then it just boils down to merging 2 sorted lists, which of course we can do in linear time in the size of the lists. Okay? So homework. Can implement in big O of the sum of the sizes of these Pareto curves, okay, from I equals 0 up to n. All right, so that's straightforward. Okay, it'd be easy to do in lecture, but I just want to make sure you understand this algorithm, so I'm going to ask you to just write the details as part of homework. Okay. So and again, I want to emphasize this is, I mean, there's a knapsack algorithm. You know, it's not a dynamic programming algorithm, at least not explicitly. Okay. So is it any good? You know, how should we interpret this running time? Okay, so what? Some of the Pareto curve sizes. Is that good or is that bad? Well, it depends. So let's start with the good news, or the first piece of good news. So if we think about this quantity, so how big could this be? Okay. Well, let's just put a factor of n up front right away for the n plus 1 sum n's. Okay? And now let's just focus on a single Pareto curve, like let's say the last Pareto curve. Okay? So, and let's think about various upper bounds we could state for how big a Pareto curve could be. So certainly, in the worst case, it's all possible solutions, of which there are 2 to the n. Okay? So we'll put a 2 to the n there. And again, it's an NP-complete problem. We are expecting to see some kind of exponent somewhere in the worst case. Now, when you study dynamic programming algorithms for Knapsack, you always assume that either the values are integers or the weights are integers. Because you have to write down this table, and you have to have columns which correspond to the possible different values or the possible different weights that suboptimal solutions to subproblems could have. And so then you get running times which depend on either the largest weight or the largest value, depending on whether you're assuming weights are integral or values are integral. So let's think about now this algorithm under this analogous assumption. So let's suppose the weights were all integers, okay? And that the biggest weight was W max, okay? What I want you to notice is I erased the definition of domination, but if you have 2 different solutions with exactly the same weight, okay, you're going to throw one of them out. Okay? Either they're both exactly the same, and then it doesn't matter, you just keep one, or one has a higher value, and you throw out the one with the smaller value. So in other words, as you generate these Pareto curves, always discarding dominated solutions, at every single step you will retain at most one solution for each distinct total weight. Okay? If weights are integers, at most W max, the number of distinct total weights of subsets you'll ever see is n times W max. Okay? So if W max is small, then you're, like say W max is just like 10, okay, and the number of items is 100, you're never going to remember more than 3,000 different items. Okay? Everything else will be dominated by something already in the set. Okay? So without changing the algorithm, okay, so without actually changing the algorithm to make use of this assumption that weights are integers, we can just automatically say that its running time is upper bounded by n times W max. Okay? Because again, that's the maximum number of distinct weights you'll ever see of different feasible solutions. Exactly the same reasoning applies to this same algorithm if the values are integers. Given 2 different feasible solutions with equal value, one has smaller weight, and that's the only one you're going to bother to keep. The one with higher weight is dominated, and you'll throw it out. Okay? So if the values are all at most Vmax, the number of distinct solutions you need to keep around is at most n times Vmax. Everything else will be dominated. Okay? So for this same algorithm, we can also write down n times Vmax. Okay? So what's cool about this is not only do we not do explicit dynamic programming, but we don't need to write down a different algorithm tailored separately for the case of integer values or integer weights. This common algorithm just automatically achieves the best of both of those cases. All right? So like in 161 when I teach it, normally I do one of the dynamic programming algorithms in lecture, and then I ask, usually in the final exam, for students to figure out the other one. Okay, but it's a different algorithm. It has exactly the same sort of template, but it's really not the same algorithm. Okay, you write down a different table. All right, so that's cool. So that's the first reason I'm teaching you this algorithm, is just because I think it's sort of a neat underrepresented algorithm. The main reason I'm teaching it to you is because actually this has a very good smooth complexity as well. Okay, and so that's the main point. I do want to point out, and I'll ask you to work this out on homework, that in the worst case, indeed we can have the size of a Pareto curve can be exponential in the number of items. Okay, so it can be the case in the worst case that none of the possible feasible solutions, none of the possible subsets of items dominate the other ones. They could all be incomparable. Okay, so I'll ask you to think that through. So in the worst case, we're not going to get a better upper bound, but I'm going to show you that if we have a smooth instance, then we actually get a polynomial bound. Okay, and that's the main point of the lecture. Okay. All right, so any questions? All right, let me state formally the main theorem. So this is from 07. There were some weaker results known earlier. So for smooth instances, and I'll explain what I mean by that. It basically means the same thing as last lecture when we were talking about TSB. So for smooth instances, the expected size, so again, in the worst case, the Pareto curve can have exponential size, but the expected size is only quadratic in n. Okay? That's what we're going to prove. Sigma, as usual, is some measure of the size of the perturbation. And again, we are expecting some dependence on 1 over sigma, because we know in the worst case, these things are exponential. Okay? So by linearity of expectations, then, this is just n cubed over sigma. Okay? So the expected running time of this knapsack algorithm is O of n cubed over sigma. Okay? And that's actually pretty cool, because, I mean, this is an NP complete problem, actually, right? So I'm giving you a polynomial time algorithm for an NP complete problem. The rub, of course, being this is not polynomial time in the worst case, but it's expected polynomial time, assuming inputs are drawn from any distribution which is sufficiently diffuse in the same sense as on Monday. So that's kind of neat, because now for the first time, smooth analysis is really telling us something not just about the performance of a single algorithm, but it's really telling us something interesting about a computational problem. Okay? So remember, a computational problem is defined independent of any algorithm. That's like the knapsack algorithm. And then you can discuss the performance of particular algorithms. And the complexity of a problem is basically the best algorithm for the problem. So it's, I mean, even forgetting about this very natural algorithm, it's just amazing there's any algorithm that has polynomial smooth complexity for this NP complete problem. I mean, now we sort of understand why, but this was sort of an interesting insight, I feel, that smooth analysis gives us. This also corroborates well with sort of empirically, knapsack is indeed one of the easiest in practice of all of the NP complete problems. So it does seem reasonable that theory would give us a result like this. Okay. Okay. Yeah, and good. Good. Right. And because, oh yeah, the other thing I want to say is, so homework. This upper bound is in fact optimal, or is tight. Okay? So I'm only going to ask you to prove it when sigma's constant, so I'll just ask you to prove a lower bound of n squared in an average case model. But the exponent in the n here is indeed correct, so it's also satisfying. Andy?
Do you see that kind of performance in practice too? Like when we got linear in practice, but it's like to the 6th power in theory or something like that?
That's a good question. I mean, so this is going to be, I think you pick up this n squared even for the uniform distribution, if memory serves. So this should match empirical performance up to constant factors. And I mean, I'll show you the whole analysis. So the constant factors are not overly large. So I haven't explicitly seen an empirical study, but just the mathematical results are so sharp here, you'd expect empirical performance to hew to it fairly closely. Yeah. Good question. So right, of all the smooth analyses I'm going to show you, just like a quantitative level, this one's the most satisfying. This one, we're really going to feel like we nailed the problem in today's lecture, which is great. Other questions? Okay. So perturbation model, let me just be clear on this. So one thing that's interesting is actually, so remember these two parameters, is the values and the weights. The values we're not going to smooth at all. Okay, so the values can just be picked worst case by an adversary. Okay, so the VIs are adversarial. And the knapsack capacity is also, well, I guess we're just analyzing Pareto curve, so we don't have a knapsack capacity. And then the weights are smoothed. So each WI, so the weight of the ith item is drawn according to a density function. Let's think of these as just in 0, 1. That's without loss of generality. We'll just scale them. Okay, so real numbers in 0, 1. The weights we'll also think of as being in 0, 1. And the definition is exactly the same as last time, where the only thing we assume about the distributions is that they're not too spiky. Okay, so the density function at a given point is at most 1 over sigma, where sigma is this parameter. Okay, so again, you can think of this as the area of the support. You can think of it as a lower bound on the amount of the unit interval that the density function has to be supported on. Okay, at least sigma.
do this the other way? Like have adversarial,
You can.
adversarial weights?
You can. Yep, so you can flip them as well. Yeah. Yeah. So what's important is just that one of them's random, and that's all you need. Yeah. Okay, so this is really exactly, I mean, in some sense, it's even simpler than Monday, because Monday, remember, we were dealing with points in the plane. We were talking about the local search algorithms for TSP. And so this is the same, just now we have one coordinate instead of two coordinates. Okay, so otherwise it's exactly the same. And again, what's cool about this is really, we don't care if this is uniform, exponential, truncated Gaussian, whatever. Okay, so there's really no dependence on the analysis on some parametric form of the distribution, right? So we don't have to assume Gaussian. So that's very nice. Because I think it's easy to believe that data has randomness in it. It's harder to believe any particular model of that randomness. So these are really exactly the kind of theorems I think we should aspire toward. Okay. Good. So, everyone ready? We're going to start talking about the proof of this theorem, or how we're going to do it. All right. So I'm going to sort of gradually, I'm going to start with just trying to help you think about the analysis in the right way, and then we're going to slowly, add the necessary complexity to actually prove the theorem. So here's the picture I want you to have in mind. So let n be the number of Pareto optimal solutions, i.e. the population in the Pareto curve. This is what we want to prove an expectation is at most that. Okay, so we want an upper bound on capital N. And I want you to think about a table, basically just kind of a discretized picture of what I just erased here. So we have these 2 to the n subsets of the items, okay? And we're looking at their values and we're looking at their weights. Remember, actually, for any subset of the items, we actually know their value exactly, okay? And it's just their weights are random, all right? So this is a random variable because the weights are random. And so the total weight of a subset of items varies anywhere from 0 to n. Remember, we're now assuming weights are between 0 and 1. And the values also, think of as between 0 and n. And we want to count how many Pareto optimal things show up here. And it's going to be convenient to break this square into slices of width epsilon. Okay? What is epsilon? Epsilon is a parameter that we're going to choose for convenience in our proof. Okay, so epsilon is not part of the input. Epsilon is just going to be internal to our proof. So we're going to break the weight range, 0n, into tiny slices. Think of epsilon as very small, of width epsilon. So there's n over epsilon slices, okay? And what we're doing here for convenience is we're going to choose epsilon so small that the probability is essentially 0 that you're going to see 2 Pareto optimal solutions in the same slice, okay? So think of there being like a doubly exponential number of slices or something like this. And then there's just going to be a merely exponential number at most of subsets showing up here. So there's no way or almost no way you'll get 2 in a common slice, okay? So what we want to do is instead of counting the number of points with multiplicity, we just want to kind of count without multiplicity. So we just want to know how many slices have at least one resident, okay? And again, this is just it simplifies what we have to do. That's why we're doing it. Small enough so that we have essentially 0 probability of greater than 1 Pareto optimal solution in a slice. Okay? And again, remember what the picture is going to look like. So the undominated points, basically nothing should be to the northwest. So it's going to look something like this. Right, so each of these Pareto optimal points, each of these red points is going to be in some slice. And n, the number of Pareto optimal solutions, given that epsilon is so small, is basically just the number of occupied slices. Okay? So that's what we want to do. We have these slices. There's some probability that it has an occupant. There's n over epsilon slices. So we want to say the probability that a given slice has an occupant is small. Okay? Right, so let me just mention right now, I mean, epsilon's not going to appear in our final bound. Okay, in our final calculations, epsilon will just cancel out. That's why we don't care what the value is. And we can make this assumption without any harm. Okay, so what's the plan? So ultimately, we need to upper bound capital N, or rather its expectation. And we know n can be big in the worst case. It could be 2 to the little n in the worst case. We need to use the fact that the weights are random, that the instance is smoothed. And it's not really clear how to directly apply the smoothed hypothesis to capital N directly. There's just like too many moving parts. Okay, so a given feasible solution, it might or might not be Pareto optimal. Its value is fixed, but its weight's random. So whether it's Pareto optimal or not, whether it's dominated by someone else or not, it depends on the coin flips for its own weights. So items, right? So think about just like items 4, 7, and 10. Okay? The subset of items 4, 7, and 10 might or might not become a Pareto optimal solution after we flip the coins. What does it depend on? Well, it certainly depends on the random weights of 4, 7, and 10. The smaller these weights are, the more likely this thing is to be a Pareto optimal solution, right? It's going to be better. Okay, its value is fixed. The smaller the weight, the better the thing is. The more likely it's Pareto optimal. But actually, it doesn't just depend on 4, 7, and 10, right? Like, we also care about whether it's dominated by other solutions, right? So it's also more likely to be Pareto optimal if other solutions have high weights, okay? And so then the question is sort of like, okay, this one has 4, 7, and 10. This other thing is 4, 12, and 14. And then you have to know who dominates who. And then, of course, there's an exponential number of other things that might dominate you. It just kind of quickly gets out of hand. Okay? So what we have going for us is that weights are random. It's just capital N is just too much of a mess to really make direct use of it. Okay? So what we have to do in the proof is we have to decompose capital N. Okay? So we have to have ways of counting Pareto optimal solutions, or perhaps over-counting Pareto optimal solutions, until we can finally actually use, in a useful way, this hypothesis that rates are random. Okay? And if you think about it, we were actually basically doing that exact same thing on Monday, although it maybe didn't seem quite as complicated. But again, the whole point of the proof was to sort of zoom in on a relevant bad event and define it just so that it was very easy to use the smooth hypothesis. So what we did on Monday, we were worried about bad swaps, okay? Swaps that don't make much progress. So we fixed a particular swap, meaning these 4 points, right? So that was good. We zoomed in on these 4 points. We actually zoomed in on a linear combination to get rid of those absolute values. And then we conditioned on 7 of the 8 relevant coordinates. And all of a sudden, it got really easy, right? We had this relevant event that this thing landed in this interval. We had this one remaining random thing, which was a single coordinate of a single point. And at that point, we just said, dude, it's random. It's very diffuse. It has a low density. So the chance that this thing lies in this fixed interval is small. Right? So really, the whole point of the proof was building up to this effectively almost trivial application of the smooth hypothesis. Okay? So that's what we have to do again today. Okay? And at the very end of today's lecture, we'll find ourselves in a position where we can just very easily use the fact that the weights are random. It's going to take us a couple steps to get there, because n is such a mess. Okay? All right, so that's the plan. So what I want to do first is I want to do kind of a baby version of the proof. So what I'm going to say for the next maybe 10, 15 minutes, we're not actually going to use directly, but we're going to build on it to do the full proof. Okay? So think of this as kind of the scaffolding which we'll refine for the proof proper. Okay, so warm up. So think about a slice boundary. I'm going to call it T. Right, so maybe it's like right here. Okay, so T is just some number, some multiple of epsilon between 0 and n. Okay? Now, intuitively, what we're going to do is we're going to look eastward from T. Okay? We're going to look to the right. And we're going to say, what's the first Pareto optimal point, the first red point that we see to the right of capital T? Okay? And basically, if it's in the slice immediately after T, between T and T plus epsilon, we're intuitively going to charge that Pareto optimal solution to this slice boundary T. Okay? So put differently, every red point, every Pareto optimal solution, we're going to charge it to the slice boundary immediately to its left. Okay? And then we're going to count up the number of slice boundaries that have these red points right next to them. Okay? So how do we say that a little more formally? So what we do first is we look to the left. Okay? So basically we're going to have notation which basically talks about these 2 points. Okay? The Pareto optimal points immediately to the left of t and to the right of t. So PT is going to be to the left. So max value solution, so the highest point, the northernmost point, to the left of t. Okay, so in this picture, that would be that red point there. That's PT. Okay? And then VT is going to be its value, or its height. Okay? Now, PT is random, okay? Because a given subset of items, 4, 7, and 10, it might or might not have weight at most t, depending on how the coin flips show up for the weights. Okay? Given PT, conditioned on PT, its value is then fixed, right? Because remember, the values are not random. The values are just given. Okay? Okay? And so now what we do is we say, let's find the next Pareto optimal point, looking to the right. Okay? And of course, as we go to the right, the weight is only increasing. So whatever the next Pareto optimal point is, it has to have strictly higher value. Okay? Otherwise, it would be dominated by the previous one. Okay? So we're looking east, and then of course we have to be looking north if we're staying on the Pareto curve. So ST, right, and so then, right, so ST is the min weight solution. So the first one we find, looking eastward, with value bigger than VT. Okay? So this would just be, right. So think of that as PT, and this as ST. Okay? Now remember, we're trying to compute capital N. We're trying to calculate the number of Pareto optimal solutions. And here's how I'm going to decompose that messy sum. Like I said, we're just going to look slice boundary by slice boundary, and we're only going to count something when it's in the immediately next slice. Okay? So NT is just an indicator random variable. 1 if, when we look eastward and find ST, it's in the first possible slice between t and t plus epsilon. If it's further down, 0. Okay, it's going to get charged to some other slice boundary later. So 1 if weight of ST is in the first possible slice, t plus epsilon, or 0 otherwise. Okay? So that's all the notation. All right? And again, for this warm-up, I'm doing something which, if you can survive the notation, I think is pretty easy to see. But the point is we'll use a slightly more complicated version of this argument to actually prove the theorem. And I want to just sort of get you used to the flavor of argument before we do the full-blown thing. Okay, so warm-up claim. So again, what are we trying to accomplish? There's capital N, we don't know how to analyze it, we're trying to break it down into simpler parts that hopefully we can analyze. So I want to say that these n sub t's are a legitimate decomposition of capital N, okay? So I want to say that if we sum up all of these indicator random variables, slices t and t, then we capture all of the Pareto optimal points. Okay? This actually holds with equality for this warm-up lemma. We don't need that. We just need to make sure we're not undercounting, okay? Okay, so this is pretty much, true by notation, but let me go through it just so the notation sticks. So proof. So suppose S is on the Pareto curve. Okay, so this is with probability 1, by the way. So these are both random variables, the number of Pareto optimal points, and whether or not there's a point in this slice t plus epsilon, because the weights are random. Okay, so suppose we have a Pareto optimal solution. That is, suppose S contributes to the right-hand side. We just have to show that S also contributes to the left-hand side. Right? So, when we sort of talk through this, since S is Pareto optimal, since its weight is bigger than t, and so in particular its weight is bigger than that of p sub t, this value, its value better be bigger than p sub t's. Okay? Otherwise, S sub t would be dominated by p sub t. Right? By definition, S sub t is to the right, so it has to be above. Okay? So, value is greater than v sub t And then remember, we're going to assume for the rest of the proof that every slice has at most one Pareto optimal point because we've chosen epsilon so small. So since there's at most one Pareto optimal solution per slice, the claim is that S has to be equal to S sub t. Okay? So we started with something on the Pareto curve. We're calling it capital S. Okay? Whoops. Forgot to tell you what t is. Let t equal slice boundary to the left. Okay? So in the definitions, I started with t, and then I made all these definitions. Now we're starting with some point of the Pareto curve, S. Okay, it's just somewhere. It has some weight, it has some value. I'm defining t to be the slice boundary immediately to the left. And then I'm arguing that in the sum on the left-hand side, we are counting this Pareto optimal solution. We're counting it through n sub t. Why is that true? Well, so what is S sub t? Let's remember what nt is 1 if and only if S sub t, which is the minimum weight solution, okay, with value bigger than v sub t. So in other words, the first Pareto optimal point when you look right. So n sub t is 1 if and only if that first Pareto optimal solution further to the right lands in the slice boundary. Okay? But that is true, just by definition. Right? So t is chosen to be the slice boundary immediately to the left of S. So n sub t for that value of t will be 1. Okay? Because S sub t is there. And we're not doing any undercounting because every slice has only one occupant, only one Pareto optimal solution. Okay? So again, this is sort of, if this feels close to vacuous, you're right. Okay? But the next version is going to be actually pretty subtle. But it'll follow exactly the same kind of template. Okay? So again, just to summarize, really what we're doing, we're saying, well, rather than count these directly, let's just charge the existence of each Pareto optimal point to the boundary immediately to the left and count those instead, okay, in this way. All right. Now, unfortunately, so this reduces upper bounding the size of the Pareto curve to upper bounding the expectation on the left, i.e. upper bounding the probability of these indicator events n sub t. So what does n sub t say? Okay, so n sub t is the probability that one of these Pareto optimal solutions lands in this particular slice. But again, that's a little complicated to understand, right? And the reason it's complicated to understand is that a lot of different possible solutions after the coins get flipped are eligible to land in this slice t plus epsilon. So we'd love to say something like fix a slice t plus epsilon. It's very low probability anything will wind up here, and then just sum up over all the slices and be done. And the issue is there's sort of 2 to the n possible subsets of items out there. And what if a lot of them have unperturbed weight really close to t, and thus have a legitimate shot of winding up with total weight in this slice t plus epsilon? Then that's a lot of different events that could happen that are all bad, and it's hard to get a handle on that. Intuitively, it seems unlikely that all these exponential number of different subsets could simultaneously be Pareto optimal while landing in the slice, but it's a little hard to figure out how to tease that out. Okay? But so that's what we're going to do by decomposing this sum even further. Okay? Basically, we get at that issue. All right, so any questions about sort of the warm-up version? Okay. Good. Then let's refine this. So here's the real proof. So we're going to have similar definitions to this, just a little bit extra complexity. All right, so proof of the real theorem, that the Pareto curve is the most n squared over sigma in expectation. So, some definitions. So T is as before slice boundary, but now in addition, we're going to parameterize by an item. Okay, so before we were basically charging the presence of a Pareto optimal solution to the boundary slice immediately to the left. Now we're going to be charging it to a combination of that same boundary slice T plus an item. And I'll show you what the item is in a second. All right, so define. All right, so before PT was you look left and you see the first Pareto optimal solution that you find. Okay? So now it's going to be a little bit different. It's going to be the max value solution. So we look left and we look up, but we restrict attention to solutions that exclude this item I. Okay? So first of all, weight is at most t, so we're looking left, but it does not include item I. Okay? So PIT may, so remember, before we define PT is just the max value solution looking left. Okay? So PIT may or may not equal PT. Right? So if you just optimize value looking to the left, maybe you get lucky and the optimal solution doesn't include I anyways. And then it's also optimal for this problem. On the other hand, maybe you get a strictly smaller value solution by adding this constraint that you're not allowed to contain I. Okay? So PIT may or may not be the same thing as PT was before. Okay, so VIT is the value of PIT as before. Now the analog of ST is again going to be sneaky. So this is where last time we sort of looked to the right of T and we just found the first Pareto optimal solution. Now we're going to restrict attention to solutions that include item I. Okay? So we look at the min weight solution. So as far to the left as possible, such that the value is bigger than our target, VIT, and 2, it includes item I. Okay? Probably you're wondering, where did this come from? Why are we doing this? So at the end of the proof, you'll see how cleanly we're able to apply the assumption that the weights are perturbed. So the way you'd come up with this is you'd say, okay, I know what I want the end of the proof to look like. I know I want some very clean application of the perturbation, and then you would back out what kind of event you actually can apply it so cleanly. That's, I think, the only way you would really come to these sneaky definitions. Okay? All right. And now, previously, we were charging Pareto optimal solutions to the boundary to the left, so now we're going to charge it to a combination of a boundary and to an item. So NIT is an indicator random variable, and it's 1, same thing as before. If the weight of SIT is in the slice t plus epsilon. 0 otherwise. Okay? So any questions parsing the definitions? It's a subtle set of definitions. Okay? So for example, unlike last time, it might actually be the case that, well, never mind. That's not relevant for the proof, so I'll skip it. Okay? So for PIT, we exclude item I. For SIT, we include item I. That's the key point. That's the key twist from last time. Now, instead of the warm-up claim, we're going to prove that we again have a legitimate counting, or rather overcounting, of the Pareto curve. Okay? So if we sum over the slices t and over the items I claim that we get an upper bound on the Pareto curve. And here equality doesn't hold. Okay? Here we really are going to be overcounting, but that's fine. We just want an upper bound on capital N. Okay? So let me prove the claim to you, and then once we have the claim, it'll be reasonably straightforward to finish the proof. Okay? And the reason it's going to be straightforward is because these NITs are actually something we can reason about directly given our smooth hypothesis. Okay, so again, the high-level proof, the proof plan is the same as before. We just want to say, consider any Pareto optimal solution. So it contributes to the right-hand side. We just have to show that it contributes to the left-hand side as well. That is, we just have to exhibit a choice of t and a choice of I so that that NIT is equal to 1. Okay? And moreover, that for each distinct Pareto optimal solution, we identify a different pair IT that accounts for its contribution. Okay? So it's enough to show that for each Pareto optimal solution S, so the t is going to be chosen the same as before. T is just going to be the boundary right to the left of S. So we just want to show that there exists an item I such that S equals SIT. Okay? The only thing to remember when I write that down is SIT is just this thing that the NIT is counting whether or not it's there or not. Okay? So NIT just says that, you know, some solution defined in some way shows up in the slice t plus epsilon. Okay? Again, we're assuming that each slice has only one Pareto optimal solution, so we're not going to charge more than once. So for a given t, there's only one possible Pareto optimal solution that will point to t as being responsible for it. And we just have to exhibit an item I so that indeed we are charging that Pareto optimal solution to this pair I and t. Okay. All right, good. So here's how we do it. And it's a refinement of the proof that we had last time. So first of all, so we have our S. It's right next to t. So for the first step, let's just do what we did last time. Look to the left. Find the first Pareto optimal solution you see looking westward. Okay? Call that P sub t. All right? So P sub t is just the highest, namely the max value solution to the left, so with weight at most t. And we denote its value by V sub t. Okay? So it's the same thing as it was before, P sub t. Now, S, because it's Pareto optimal, and because it has higher weight than PT, S has strictly more value than PT. Okay? Therefore, there's got to be at least one item which is in S, but not in P sub t. But it's got more value. There's got to be some item which is the reason it has more value. Okay, it's not some subset of PT. Any one of those items is going to serve as our magic item I. Okay? So since S is Pareto optimal, with weight bigger than t, in particular weight bigger than P sub t, value of S is bigger than the value of PT. And so there exists an I that lies in S, but not in P sub t. Okay? So remember, we started with the Pareto optimal solution S. How did we choose T? That was the boundary just to the left. How did we choose I? We picked an arbitrary item in the Pareto optimal solution S and not in the next Pareto optimal solution looking west, looking left. Okay? So given S, we chose I, we chose T. We're going to show that for that choice of I and T, indeed, the indicator of random variable NIT counts the Pareto optimal solution capital S. And that's just what we needed. We just needed to show that, look, for each choice of I and T, we're counting whether or not something exists. And we just wanted to show that everything on the right-hand side is covered by somebody on the left-hand side. So we've taken S, I've shown you the I, I've shown you the T. All I have to argue is that NIT equals 1. Okay? All right, so for such an I claim the following. So first of all, I claim that PT and PIT are the same. Now, what are these things? I know you've forgotten. All right, so PT, that's just this. Okay? We looked westward. We found the highest point we could find. Okay? What was PIT? So that says, oh, by the way, I also force you to exclude I. Okay? So this was the thing that might or might not have been equal to PT. It depends. Okay? Whether or not the optimal solution with weight at most T needed I or not. We've chosen I so that the optimal solution to the left doesn't contain it. Okay? So this restricted optimization problem, PIT, okay, so the max value thing excluding I, it's actually the same as the max value solution unrestricted. Okay? That's by choice of I. Okay. So that doesn't matter, excluding I or not, we get the same thing. Then of course it means that the values are the same. right? Because it's just the same set of items. Items just have some values, so you get the same set of items. So that means when we think about the definition of SIT, which I'll remind you of what it is in a second, it doesn't matter whether I write VIT or VT here. It's the same number, okay? Now, I claim that, in fact, SIT, the thing that NIT is counting, okay, SIT just equals S, the Pareto optimal solution with which we began, okay? If I can argue 3, we're done, okay? Because then that really says this Pareto optimal solution is accounted for in the indicator random variable NIT. So why is this true? Okay, well, let's remember what the definition of this is. Okay, so what is this thing doing? So SIT says, okay, find the minimum weight solution whose value exceeds some threshold. Okay? In this case, the threshold is just the value of PT. Okay? So in other words, and then also it has to include item I. Okay? Now again, by our choice of the item I, when we look right to minimize weight, it doesn't matter whether we insist on including I or not. Okay? We chose I to be an item that the optimal solution includes anyways, even in the unrestricted case. Okay? So that means, and this is just like in the warm-up claim then, so you look at, right, so now you're basically looking to the right of T, you're looking for the first Pareto optimal solution that you can find. It doesn't matter whether you're forced to include I or not forced to include I. And there is S sitting there in the first available slice between T and T plus epsilon. Okay? And that's exactly what triggers this event. Okay, what triggers this event is looking to the right. Do you see what you're looking for in the first available slice, or do you see it furthermore to the right? Okay, S is right there in the first available slice. We chose T to be immediately to the left of it. So S, because of S's presence, because it's equal to SIT, this will be equal to 1. Okay? So therefore, NIT is equal to 1. All right. So that's why it works.
It feels like it's going to be a loose bound because you're going to be overcounting S like many times for each item.
Absolutely right. So it could be off by a factor of up to little n. Yeah, I completely agree. Okay. Although, like I said, at the end of the day, the bound we get is tight. So it will overcount in some cases, but overall it only matters by a constant factor. Okay. All right, so that's sort of a very, so there's two very clever parts of the proof that interface together. You've seen one of them. This fact that if you look to the right and you look to the left and you choose this I carefully, you can get away with imposing these extra constraints. You can impose the constraint that you exclude the item when you look left. You can impose a constraint that you do include it when you look right. And it actually doesn't change the optimization problems if you choose the item I just so. If you choose it to be something that's in the right, the sort of easternmost Pareto optimal solution and not in the one on the west. Okay? Now, why is that useful? That'll become clear in a second. Okay? All right, so having proved that, we can now forget about it. And the point is, given that this claim is true, it reduces upper bounding the size of the Pareto curve to upper bounding the expected value of the left-hand side. Okay? And by linearity of expectation, that just means we need to understand the individual expected values of the NITs. Now the NITs are indicator random variables, so really what we need to understand is the probability that a given NIT equals 1. Okay? All right, so to finish, by linearity of expectation, we just need to prove that the expected value of NIT is at most epsilon over sigma for all IT. Let me ask you, how many different such random variables do we have? How many choices do we have for I? N items, right? So n choices for I. How many choices for T? Do you remember? It's been a long time. N over epsilon. Right? So we had the total weight range from 0 to n split up into multiples of epsilon. Okay? So there's n squared over epsilon terms on the left-hand side. Okay? So if we prove an upper bound of epsilon over sigma for each, then that gives us a bound at the end of n squared over sigma. Okay? Since n times n over epsilon choices for IT. Okay? So as promised, the epsilons are just going to cancel. Okay? Does everyone agree with that? If we can prove this for every single IT, just by linearity of expectation, we get our n squared over sigma bound. Okay. So i.e. we want to prove that the probability that NIT equals 1, also known as that SIT is in t plus epsilon, is the most epsilon over sigma. Okay? All right. So SIT is wherever it is. It may or may not be in the slice, TT plus epsilon. Let's figure out the probability that it is, in fact, in that very slice. All right. And now, basically, all of the work we've done so far has been in service of making this last step easy. Okay? So, fix I and T. And we're going to go ahead and condition on all of the items' weights except for the weight of the ith item. Okay? So we have n items. All of them have random weights. We're going to leave just this one residual random weight. The other n minus 1 will fix. So we're going to prove the stronger statement of an upper bound on this probability for every possible fixed setting of the weights other than I. In other words, the item I alone has enough randomness to allow us to prove that this bad event is unlikely. Okay? This is very similar to what we did last lecture when we had these 8 coordinates and we fixed 7 of them, and the 8th one was enough randomness to have the probability of a bad swap be small. Okay? So again, so we're boiling it down to just a single random thing. Okay? Now, here's where things get really nice. Okay, here's where sort of the genius of this proof really starts shining through. The only thing that remains random is the weight of WI. All right? So I claim that actually then, even though it seems like SIT is a crazy complicated definition, actually this event's super easy to understand, okay? With everything fixed except for I's weight. So let's just go through step by step. How is SIT defined? So the first thing we do is we look to the left of T, and we say, what's the optimal solution that excludes I, the max value solution that excludes I? So this is optimizing only over solutions where I is not a member. I is the only thing that's random at this point, okay? So we have fixed values, we have fixed weights, okay? So we know exactly which solution PIT is at this point. Okay? It's deterministic, okay? So PIT is fixed. And that's because that's by its definition. And this is now you're seeing why we defined it this way. The reason we wanted to exclude I is because we wanted these to be just deterministic. And so therefore also VIT is fixed. Okay, so the values are always deterministic, so once you know the items, you know the value. Okay, so P is just a set, V is just a number. Now let's look at SIT, okay? So what do we know about SIT? So for SIT, it says, well, we are only going to consider solutions that have sufficiently high value, okay? But VIT is fixed, is deterministic, and values are deterministic, so we know exactly which subsets of items have values strictly bigger than VIT, okay? Moreover, for solutions that include I, now it's true that we don't know exactly what the total weight of one of these solutions is, right? Because I is still random, okay? Maybe it's 17, maybe it's 23, who knows? On the other hand, think about taking all the solutions that include I and sorting them by weight. Or put differently, just think about the relative order in total weight of everybody that includes I, okay? This ordering, total ordering on solutions that include I, we know completely at this point, okay? And that's because there is only one item which is random, that's item I. Okay? It might be 17, it might be 23, it might be 47, but it's 17 or 23 or 47 for everybody, okay? So we look at the solutions that include I, we look at their total weight for stuff that doesn't include I, we sort them in that order. That's still their relative order once we put I back in, okay? Because it has the same value for everybody. So for solutions that include I, the ordering by weight is fixed. Okay? So what do you think? SIT. Is there any randomness left in SIT? Think about it for, take 60 seconds to think about this, okay? I'm just asking about which, so remember SIT is a set of items. It's something like items 4, 7, and 10, okay? And I'm asking at this stage, is there any uncertainty left in what the set SIT of items is? Who votes yes? Who votes no? Okay. Then I guess it was a good question. There's some disagreement. So let's try to argue why, just in terms of the set SIT, why it's actually completely fixed at this point. Why there's actually no uncertainty about what the set SIT is. All right. So first of all, who's eligible to be a set of SIT? So you've got to have item I. Okay, that's deterministic. You give me a set of items, I know whether I is in it or not. You have to have total value at least VIT. Okay? We argued that VIT is known. Okay, that's just a number, 1024, whatever. And of course, the values for all of the items are just known. They're not random at all. Okay, so you show me, so given that this is just some number, you give me a set, I know whether or not it satisfies this condition or not. Okay? So the feasible solutions, if you will, the subsets of items that satisfy constraints 1 and 2, is fixed. Moreover, their ordering by weight is also fixed. We don't know, this is what we don't know. We don't know exactly what the total weight of a given subset is, but we do know its total weight modulo item I, and that's enough to know the relative ordering. And so what is SIT? It says amongst all of the subsets which satisfy properties 1 and 2, which is some deterministic list, find me the one with the smallest weight. Okay, and that's a property only of the relative ordering by weight. Okay? So this is where things glue together just beautifully. Okay? So conditioned on all weights other than the ith one, we know exactly which item set is SIT. Okay? So SIT is fixed. Okay? So what is unknown, only its weight, which has the form x plus wi, is random. Okay? So capital X here denotes the sum of the weights of all of the items other than I in SIT. Okay? So that's fixed, and then there's the random weight of wi. Okay. So, okay, now what was the event? Okay, so the original event was the probability that some random subset falls in some slice. Okay? I see. But I guess I should say the value of. Anyways, yeah, you know what I mean. Okay, so that the weight of that lies in the slice t plus epsilon. Weight of SIT. And so initially when we're looking at this event, what seems so intimidating is not so much the randomness in the weights, but rather the randomness in who SIT is. Right? So we had this elaborate labyrinth of definitions leading up to some crazy definition of what SIT was. That's what seems scary. Like, how do you know whether this is items 4, 7, and 10, or items 6, 7, and 12, or whatever? And what we're actually saying is actually at this point we know what the set of items is. And moreover, there's just one random weight left. So, of course, if you tell me exactly which items these are, and the only question is whether the total weight lies in this interval or not, now it's exactly set up, it's exactly in the wheelhouse of our smooth analysis assumption, right? This weight is random. The density on any given point is at most 1 over sigma. Okay, there's a Lebesgue measure only epsilon in this interval. So, integrating over all of the different values for the weight of item I that would send the total weight of SIT into that interval, we get at most epsilon times 1 over sigma. Okay. So, since Fi x at most 1 over sigma for all x by assumption, the probability is at most the interval width times the density epsilon over sigma. So that's the proof. Okay. And so again, I mean, it's really a masterful, sort of a master class in how to cleverly organize the counting or overcounting of something in a way that you break it down into these little pieces. So for each little piece, it's actually very easy to relate it to the randomness assumption on the input that you have. Okay? So, and like I said, I don't think it's an accident that there were some weaker versions of these results proved first. This wasn't sort of the first proof that people working in the field came up with. This is more kind of the proof from the book after they understood it really, really well. Okay? I guess the final comment, so this was just for knapsack. So there were effectively 2 linear objective functions. You were talking about the weights and you were talking about the values. So just in the past few years, so since the last time I taught this class, there's been some very impressive follow-up works where they talk about higher dimensions. So you can talk about Pareto curves, of course, not just in 2 dimensions, but in multiple dimensions. So now one point would dominate another if it's better in every one of D coordinates. So you're undominated if for each other point you're better than it in at least one coordinate. And so so what happens is you get that the Pareto curves get bigger with the dimensions, exponentially in the dimensions, but at least n is still polynomial. So if you have D linear objectives, here we had n squared over sigma, and there the upper bounds become, everything just gets raised by D. So it's n to the 2D over sigma to the D. And it's known that that's close to tight. So you need the sigma to the D dependence, and it's known you need n to the D dependence. So the only gap is between n to the D and n to the 2D. So that's, so there was a paper by Moitra and O'Donnell in Stock 2011. There was a paper by Roglin and a co-author in Stock 2012. So this is stuff that, people are just doing some very impressive new results just over the past few years on exactly this problem. Okay, but this is kind of, if you just wanted to know one result in the field, sort of in this subfield, I think this would be the one about Pareto curves, n squared over sigma. Any questions? So Monday will be probably our final smooth analysis lecture, and that will be just really about one theorem that's a very cool theorem, which is more in the spirit of complexity than of algorithms, so really understanding properties of problems rather than properties of algorithms. And it's in some sense a generalization of this knapsack result. So we're going to study problems which are solvable in pseudo-polynomial time. So that's a generalization of knapsack, which is solvable in pseudo-polynomial time. And we're going to show that within a certain class, whenever you have a pseudo-polynomial time algorithm, you automatically have polynomial smooth complexity. And not only that, but there's also a converse. So if you have polynomial smooth complexity, then you're also solvable in pseudo-polynomial time. So it's almost like a novel type of complexity class. Solvable in pseudo-polynomial time equals solvable in smooth polynomial time. So that'll be Monday. Have a good weekend.